Hi there, Biochemistry 1 students. This is the first week video for fall of 2024, and I'll preview a little bit of what we're going to be getting into in the later part of week 2, hopefully. Video will try to keep it to like 20 minutes or so, and the idea here is I go fast. That's because you can slow me down, you can speed me up, you can pause me anytime that you need, and you can re-listen. So I'll go fast to not use up your time on parts that are easier to get through. So first of all, periodic table. We highlighted for you the first 3 rows and their importance, really the first 2 rows because they contain HONC, H-O-N-C, which are the primary elements that we find in living systems. So you should consider the first 2 rows to be the most important. Remember also that HONC tells us how many bonds these tend to make in molecules, and you saw this in the molecular modeling that we did. So hydrogen makes 1 bond, oxygen makes 2, nitrogen makes 3, carbon makes 4. If we delve a little bit deeper into the actual periodic table entry and what you might find on it, here's one that's really rich in information. But note the atomic number. Hydrogen's is 1. That tells you how many protons. There's a symbol. Hydrogen's is H. The name of the element, the atomic weight, which is an average across all naturally occurring isotopes, which is basically saying if you take all the hydrogen 1 on the planet, which most of it is, which has 1 proton and 0 neutrons, and you average that with the amount of hydrogen 2, which has 1 proton and 1 neutron to add to 2, and the tiny little bit of hydrogen 3 that exists, 1 proton and 2 neutrons, then any random sample of a lot of hydrogen from our Earth would weigh something like 1.008 because it is so overwhelmingly made of hydrogen 1. There are things like crystal structure that you might find, boiling point, melting point, density, even electron configurations that you might find in different tables. But that's the core info: atomic number, atomic mass, and then knowing different isotopes, hydrogen 1, hydrogen 2, hydrogen 3. Here's what the structure of an atom might be said to look like. This is a model of oxygen. You've got 8 protons in this oxygen. You've also got 8 neutrons. That would make it oxygen 16. And because it is a neutral atom, we're now showing 8 electrons in this model as well. When oxygen gets involved in making a molecule, there's what it would look like on the bottom using our ball and stick kits that we use to model molecules. What's happening is that oxygen is sharing 2 pairs of electrons in this case, which we call a double bond, so 4 electrons total. And that's because in its outermost ring, or shell, oxygen has 6 electrons, which is not as stable a number as 8. So as you can see, when they share, if the 4 that are in the middle kind of can be said to be on either oxygen, then both oxygens have access to 8, which is a stable situation. This is why oxygen makes 2 bonds. So again, remember, HONC rules here. Now, most important molecule that we learned some things about is a water molecule composed of 2 hydrogens, which are a proton with 1 electron, and then 1 oxygen, which is 8 protons, 8 neutrons, and 8 electrons. And in order to achieve access to 2 electrons, which is the stable configuration for hydrogen, each hydrogen makes 1 covalent bond. Covalent means electrons together. Puts its electron together with 1 electron from oxygen so that it has access to 2 electrons. Because oxygen is better at pulling on electrons than hydrogen is, this is a polar covalent bond. And the oxygen side of the molecule therefore feels partially negative, which is what that little funky delta symbol that we've been drawing means, and the hydrogen ends of the molecule feel partially positive. Result of these polar covalent bonds in water is that hydrogen bonds form between water molecules, and they form between the hydrogen of one water molecule, which is partially positive, and the oxygen of another water molecule, a different water molecule that is partially negative. These bonds are easily broken and reformed unless you try to break too many of them all at once. And my analogy there has been like belly flopping into water. Water's properties emerge from these underlying characteristics. So let's look at how. Our rhyme here was sticky wicky, not so hot, floats when frozen, dissolves a lot. The properties associated with each one, which I'm going to go through one by one, are on the right-hand side. So again, I'm going to define each of those one by one now. You can pause the video if you want to write them down. First, the sticky wicky parts. And I'm highlighting cohesion, which is when water sticks to other water molecules due to hydrogen bonding. And hopefully you're starting to recognize that's the partial positive white hydrogen in this model of water going up a tree, sticking to the partial negative red oxygen of a different water molecule. That's cohesion, when water sticks to other water. When water sticks to another molecule that has partial charges, that's called adhesion. So here, the partial negative oxygen of this water is sticking to the partial positive chunk of a tree's trunk, which is made of cellulose. So probably it's a partial negative oxygen in the cellulose molecule that this water is sticking to. We played with that using toothpicks in class. So you saw how like the wood of a toothpick, which is of course wood from a tree, can do this process of adhesion, pulling the water around by making hydrogen bonds with it. Okay. Finally, surface tension is the cohesion on the surface of a body of water. And it's a combination of like the side to side cohesion. So you can see in this diagram with the bug in the bottom right, there's side to side cohesion between water molecules. And there's also like diagonal and downward cohesion, which basically creates a difficult to break through if you're being very careful, like this water strider is, network of hydrogen bonds. So just highlighting that it's not purely horizontal direction, because that wouldn't make necessarily a ton of sense. It's also water molecules underneath that kind of hold the upper layer in a hydrogen bonding network. But at any rate, cohesion on the surface of water creates surface tension, and that allows, for example, certain organisms to remain upon the surface of a body of water. Second, not so hot. Water has a high heat capacity. Temperature, we said, is the movement in a substance. It's the average kinetic energy. Kinetic energy is energy of movement, so average kinetic energy is the average movement in a substance. That's its temperature. So if you were to look at any real molecule, it would not be sitting still. It would be doing what the molecule on the left of the screen is doing, vibrating. And if I made that molecule take on a higher temperature, it would vibrate even more. And I could get it to the point where its shape actually starts to pop apart a little bit because it's moving so much. That's sometimes why when you cook things, they change chemically. You're adding so much energy in that you make them snap apart. They move so much and they change their features. The energy that you might add into a substance to get it to change temperature is heat. So it's not itself temperature. Heat is not itself temperature. Heat is energy you can add to a substance to change its temperature. And so the analogy here is that it takes a ton of heat to cause a change in temperature in water, which is, we call it its high heat capacity. I tell you to think of this like a rugby team locked in a scrum formation where there's collective strength because of the hydrogen bonding network. It is hard to make the water move very much more. It takes an immense amount of heat to do that. The same amount of heat could be added to air and cause a way bigger change in temperature. This is a weird thing to realize. You can add the same amount of heat to two different substances and their temperature change will not be the same. The same amount of heat added to water will not be the same amount of temperature change as that amount of heat added to sand or asphalt or the air. And all you have to do is go park your car at the beach and walk across the sand to the ocean to find this to be the case. They're all getting hit by the same sun, same amount of energy per unit area. But the water remains quite cold because it absorbs the heat without changing its movement very much, whereas the pavement and the sand and the air will all get much warmer than the water could with the same amount of heat invested. Interesting thing to realize. Third, floats when frozen. On the left-hand side is liquid water. We played with this model in class on Tuesday. And on the right-hand side is what that liquid water would look like if it were no longer liquid, but instead arranged into a solid. This is called a crystal structure. So when things turn from liquid to solid, their molecules tend to organize a bit. The interesting thing about water is that the way that its crystal structure organized causes the molecules to spread out. And when they spread out, that means that there's less of them in a volume. So that means that ice is less dense than water and therefore floats in water. This is not typical for most solids. They will not do this mostly. This has huge implications for, like global climate. Ice is very reflective. So the fact that it floats actually reflects a lot of light back up to space and prevents heating. And as ice melts, things heat up quite a bit. So it's a really important, what's called a feedback in the global climate system. It's also how you get like polar bears that can live on ice, or how like a pond can freeze on the surface, but not freeze solid. When the surface freezes, the ice floats and it actually acts as an insulator for the water underneath. If the ice sank, then the surface would freeze again and sink, and the surface would freeze again and sink, and you'd much more rapidly end up with a frozen solid pond, and it would be very hard for aquatic life to exist. So these are important properties as well. Finally, water is an ideal polar solvent. This dissolves a lot. Anything that is charged can be dissolved by water. I'm going with 3 different ways of looking at one example of that here, which is how salt, table salt, chemical formula sodium chloride dissolves in water. Sodium chloride is Na plus with Cl minus. Sodium is Na, and that's the ion version of it, meaning it's given up an electron and become positive. And then chloride is Cl minus. And again, that's the ion form of chlorine, which has gained an electron from sodium and become negative. If you have a crystal of salt on the table and it's solid, you can look at it and see that it's basically like a little cube or oblong shaped cubic type structure. And the reason for that is that the sodium and chlorine arrange right next to each other, plus next to minus, next to plus, next to minus, in a 3-dimensional cube or something similar to it. There's examples of that on the top of this slide and also at the bottom left. But if you throw a sodium chloride or salt crystal into water, what will happen is the water will start to peel individual sodiums and individual chlorides off of the crystal, and the crystal will rapidly dissolve away. The way water does this is shown in the top right, where you see the partial negative oxygen of water from multiple different water molecules surrounding a positive sodium. Opposites attract, so that should make sense. And then if you look to the right, top right of the slide, to the hydrated chloride, Cl minus ion, you'll see it being surrounded by the partial positive hydrogens of water, again, because opposites attract. That's shown once more in the bottom left, where you can see sodiums and chlorides being peeled off by water with the appropriate part of the water molecule surrounding them. And you can also see it on the bottom right with our little blue hydrogens and red oxygens, partial positives and partial negatives directed toward the sodium and to the chloride. So these are the properties of water: sticky wicky, not so hot, floats when frozen, dissolves a lot. Quick preview of what we'll get into after we finish water properties and our urban heat island effect lab and how it is related to water's high heat capacity in particular. The next thing we'll start looking at is how you could do chemical reactions to rearrange some of these atoms. Okay, so for example, like on the left, we're burning hydrogen gas, H2, in the presence of oxygen from the air, and H2 plus O is making, well, water vapor. When we burn hydrogen gas, we make water vapor. There's another way of looking at burning a substance in the top right, which also shows hydrogen gas being burned. And it compares it to a different type of burning we can do, the burning of methane, CH4, which is natural gas. CH4, when you burn it, combines with O2 to make H2O, but also CO2. And so you can imagine how a lot of people are talking about burning hydrogen as a fuel might be smarter for our climate going forward because we worry about CO2. And if you burn hydrogen, you only make water. Whereas if you burn methane, you make CO2 as a byproduct, and that is a greenhouse gas. And methane, it turns out, is too. Also shown in the bottom right, sometimes reactions can be run in reverse. So if you add enough energy to water, you can make it pop apart into H2 and O2, hydrogen and oxygen. So we'll get more into these. This is the breaking and formation of bonds, and that's what we call a chemical reaction, the breaking or making or both of covalent bonds, either because you're adding energy to the system or sometimes because it's actually going to emit energy from the system, or both. So we'll get more into this next week. Here are the terms you ought to know. I'll always try to end with a slide that just like lists out all the terms. You can look up any of these and find a good definition. My hope is that if you pause the video and look at these, you should be able to be like protons, yes, neutrons, yes, electrons, yes, I know what these things are. I understand the context in our course of them. And if you go like, ions, I'm not sure I totally get what an ion is. Well, you could look up ion and read that it's an atom that has gained an electron or lost an electron. Or you can come see me at student support and be like, I don't know that I get ions. Let's talk about them, or both. So hopefully you can look down this list and find evidence of all these things in this video, as well as any additional information you might need, and then just come see me for any support that you might want on understanding any of these concepts. This is quite a lot to talk about in like a week, just over a week, really like 3 class meetings. So y'all have done a really good job with that. Stick with it. We're going to return to these concepts and understand them better and better throughout the year, and you'll continue to grow as biochemists. Thanks, everyone.